problem says the bar graph at the right shows the number of students in each of the 3 fourth grade classes at Mayfair School. If 7 new fourth graders were to start attending the school, how could they be assigned to the classes to make each class of equal size? So we are shown a bar graph of the number of fourth graders in class A, B, and C. We are asked to find how many students should be added to each class if 7 new fourth graders came to school. The goal is to make each class equal. And our plan is we will read the bar graph and find out how many students are in each class. Once we know how many students are in each class, we can find the number of students that should be added to each class. We can try different ways to assign the 7 numbers of students to the classes until we find a way that makes the class equal size. Alright, so we got to read the bar graph. So in class A, there are 20 students, okay? So A has 20, B has 20, and C has 22. Okay, and we have 7 to divide among the 3 kids, or among the 3 classes. So if 2 more students are added to each class A and B, that would make the classes 22. Okay, so let's say we're going to add 2 here. We're going to add 2 here. So now they're all 22. Okay, and we're going to put a 7 over here. We're going to cross that out. And if we subtracted 4 from 7, we have how many left? 3. Okay, so we have 3 kids from each class, or 3 kids left. Okay, and how many classes do we have? 3. So we're going to add another student to each class. So that makes 23, 23, and then this one equals 23. Okay, pretty simple.
Yeah.
So 3 students should be added to each class of A, B, and C, and 1 student added to, or 3 students to classes A and B, and then just 1 student to class C to make them all 23. We know our answer is reasonable because classes A and B we would each have 20 plus 3 or 23 students. Any questions? Okay, so today is lesson 79 and it's on symmetry. So it's in
what?
symmetry, line of symmetry.
Oh.
Okay, so the lesson says, in nature we often find a balance in the appearance and structure of objects and living things. For example, we see a balance in the wing patterns of moths and butterflies. We can call this kind of balance reflective symmetry or just symmetry. The dashes across the drawing of the moth indicate a line of symmetry. The proportion of the figure on each side of the dashes is a mirror image of the other side. So what that means is you can actually take a mirror and it should reflect exactly what from one side onto the other side. Okay, if we stood a mirror along the dashes, the reflection in the mirror would appear to complete the figure. Some polygons and other figures have 1 or more lines of symmetry. Example 1. Which of these polygons does not have a line of symmetry? Now, a line of symmetry, so they means that you can lay one side on top of the other. So here's a triangle. If we draw a line down the middle, we could actually fold this. Now my line is not directly in the middle. We could actually fold this over here and it would lay flat with nothing outside the edges. So, which one does not have a line of symmetry? Okay, yep.
C.
C, because C looks like this. And there's no way, we can't cut it in half because this isn't
both
gonna.
sides, the little slant makes it uneven.
Okay. Example B, or number 2. About half the uppercase letters in the alphabet have lines of symmetry. Okay, so the word chair looks like this. Okay, so C has a line of symmetry. H has 2 lines of symmetry. A has 1. I has 2. And R has none. Because if you lay it flat, it's not going to, right. Okay, the symmetry illustrated in examples 1 and 2 is reflective symmetry. Another type of symmetry is called rotational symmetry. A figure has rotational symmetry if it matches its original position as rotated. For example, a square has a rotational symmetry because it matches itself every quarter turn. Likewise, the uppercase H has rotational symmetry because it matches its original position every half 180-degree turn. So what they're saying is that they have a square, okay, and they can turn it and it's still, here's a fourth of a turn, and then they're going to turn it again, and this is a half turn, and it's still going to stay the same. Okay, so it has a 180-degree turn. So example 3, which figures do not have rotational symmetry? That means if you turn it, it's not going to look the same shape. So figure A has rotational symmetry because it matches its original position when you turn it. B has rotational symmetry, which is a rectangle because it matches its original position every half turn. So see up there on A, once I turned it 1/4, or a half turn, it came back to the way it looked in originally. See how A here, and then once it's a half turn, it's back to the way it was? So that's what they're talking about there. Okay, C has rotational symmetry because its original position is 1/6 of a turn. So which one does not? Timberly? D, because if you turn it, no matter what, it's got to turn all the way around before it's going to look the same. Okay, all right. Take your whiteboards out, and you have to, we'll do a couple of them. So what you have to do is copy each figure and then draw the lines of symmetry, if any. So everyone go ahead and do A.